given is this one. That is H2 plus I2, reversibly giving 2HI. All these are gases. All these are gases. Okay. This is an equilibrium given. What is the effect of pressure? Effect of pressure will be there only for gas phase reactions. That is point number one. Effect of pressure is there only for gas phase reactions. Point number one. Second, effect of pressure will be there if the number of gas molecules on both sides are different. The number of gas molecules are different on both sides. Now you come here. This is a gas phase reaction. Now you count the number of gas molecules. H2, 1 plus I2, 1. On the right hand side, 2. Say the number of molecules, gas molecules on both sides equal. And under such conditions, pressure has no effect. If a number of molecules in the gaseous state on both sides are equal, pressure has no effect. If there is difference in the number of gas molecules, pressure has effect. Then, if pressure increases, equilibrium shifts to the side where there is less number of molecules. When pressure decreases, the equilibrium is shifted to the side where there is more number of molecules. And this is that all the reactants and products you consider should be in the gaseous state. You consider only the gaseous state molecules, reactants as well as products. Here both sides, the number of molecules equal, so there is no effect. Pressure has no effect on the equilibrium. That is a choice D. Give the relation between Kp and Kc in the following reaction. The reaction is 2HI reversibly giving H2 plus I2. Now, what is the relation? Kp is equal to Kc into RT raised to delta N. And what is delta N? Delta N is equal to number of molecules on the right hand side. Gas molecules, right hand side, minus number of molecules on the left hand side. On the right hand side, total number of molecules 2. On the left hand side, total number of molecules 2. So delta N is equal to 0. So in this equation, say Kp is equal to Kc into RT raised to delta N, it will become Kc into RT raised to 0. Any quantity raised to the power 0, that is equal to 1. Therefore, Kp is equal to Kc. Kp is equal to Kc. That is choice C. In the following, N2 plus 3H2 reversibly giving 2NH3, delta H is equal to minus 92 kilojoules. So, N2 plus 3H2 reversibly giving 2NH3, delta H is equal to minus 92 kilojoules per mole. Delta H is a negative value. So, forward reaction is exothermic. And the backward reaction is endothermic. Backward reaction is endothermic. What are the favorable conditions for formation of ammonia? Formation of ammonia. So we need the forward reaction. We need the forward reaction. But forward reaction is exothermic. Exothermic. So exothermic. So low temperature is favored. Low temperature. Now, pressure. On the left-hand side, total number of molecules, 1 plus 3. On the right-hand side, total number of molecules, 2. So when we want the forward reaction, that means that a decrease in the number of molecules. So to change the equilibrium to the side where there is less number of molecules, high pressure is favored. High pressure. So the favorable conditions are high pressure and low temperature. High pressure and low temperature. That is choice A. What happens when oxalic acid is added at the following equilibrium? All of you are written, the blood red color decreases, backward reaction increases. What is the effect of a change in temperature on exothermic and endothermic? Exothermic, say when temperature decreases, exothermic increases and endothermic decreases. When temperature decreases, exothermic increases and endothermic decreases. So the choice is D. Distinguish between Lewis acids and bases. Lewis acid, electron acceptor. Lewis base, electron pair donor. Electron pair acceptor and electron donor. So choice is A. Choice is A. Now you come to the next question. That is acids and bases. Arrange the following solutions in the increasing order of hydrogen ion concentration. If a pH is given, you are given pH. pH values are given to you. And the pH values are, A is equal to 7, then B is equal to 8, C is equal to 1, D is equal to 11. These are the pH values. But in the question, you are asked to arrange in the increasing order of hydrogen ion concentration. Hydrogen ion concentration, not in the order of pH, but in the order of hydrogen ion concentration. You know, when pH increases, then hydrogen ion concentration decreases. Or when pH decreases, vice versa, pH decreases, hydrogen ion concentration increases. So which solution has the highest hydrogen ion concentration? It is for the lowest pH. So C has highest hydrogen ion concentration. Next one, the next higher pH, that is A. So the next one will be next higher hydrogen ion concentration, that is A. Then the next one will be the next higher pH value, and that is equal to 8. And the least hydrogen ion concentration, that is for the highest pH, that is D. So the order will be like this. Highest for C. So C, just wait, C greater than the next higher one. A greater than the next higher one. That is B greater than D. Or you can write in the reverse manner. D less than B less than A less than C. See, both are correct. And what is the choice given here? Choice C. A greater than B greater than, C greater than A greater than B greater than D. Choice D. See, Atul, You have written
Yes, sir.
correctly first. You did it correctly first. And then you simply cut it off. And you just reversed it. That is why you lost 1 mark. So it is not in the order of pH. It is the order of concentration. What you have
No,
done?
sir. The second answer I wrote is also correct.
Uh, no, the first time you have written correctly. It is very clear. I could see it. But you made it say wrong. You made it more correct. Okay. Now, in the following reaction, find out oxidizing agent and reducing agent. You have to get a oxidizing agent and reducing agent. Reducing agents. You consider only the left hand side. You consider only the left hand side, the reactant side. From the reactant side, you must say which is oxidizing agent, which is reducing agent. When such questions are asked, you consider only the left hand side. And what is oxidizing agent? Oxidizing agent is electron acceptor. Electron acceptor. Reducing agent is electron donor. Electron donor. You consider only the left hand side. That is Zn and Cu positive. You consider only these two. And say the reaction will be like this. Cu. And which is electron acceptor and which is the electron donor. Which is a electron acceptor. Which is accepting electron. Say Cu plus 2 is converted to Cu, then 2 electrons are accepted. So Cu plus 2 is the electron acceptor, and therefore Cu plus 2 is the oxidizing agent. Now you come to zinc. Zinc is converted to Zn plus 2. And during that process, 2 electrons are lost. So zinc is electron donor. Therefore, Zn is the reducing agent. Remember, you always consider the reactants. What happens to the reactants? Which one is accepting electron? That is an oxidizing agent. Which one is donating electron? It is the reducing agent. So Cu plus 2 oxidizing and Zn is the reducing agent. So the choice is B. What is oxidation and reduction? In oxidation number concept. All of you have written that. Oxidation, increase in the oxidation number. Reduction, the decrease in the oxidation number. Question number 11. What is redox reaction? Redox. Majority of written like this. A reaction in which there is reduction and oxidation simultaneously. So, simultaneous reduction and oxidation. And that is also an answer. At the same time, you can say there is a simultaneous loss and gain of electron. Loss and gain of electron. Simultaneous loss and gain of electron. You can write oxidation and reduction together also. One example. A majority of you have given the example for that. The choice, what is meant by ionic product of water? You are written Kw is equal to concentration of H plus into concentration of OH minus. The value also you are written 10 raised to minus 14 mole square per liter square. You are written. Define equilibrium constant Kc. Question number 12. Majority of you are written that. What is the factor upon which equilibrium constant depends? It is temperature, not a concentration. Some of you have written concentration. For them also I have given the mark, but you have written temperature. For that you are given the credit. So equilibrium constant depends on temperature, only on temperature. What happens to equilibrium point if a catalyst is added? Catalyst increases the forward and backward reaction to the same extent. So the equilibrium point is not affected. Equilibrium point is not affected by a catalyst. The equilibrium point is not changed by the action of a catalyst. It increases the forward and backward reactions to the same extent. Equilibrium is attained faster, but the equilibrium point is not affected. Then choice. What is meant by oxidation number? The definition you are written. K2CrO4 you are written. Some of you say instead of a K2Cr2O7, some of you are written K2Cr07. And finally you are go to the answer plus 6. That is from your memory you are written. Say like this. Say plus 1 into 2 plus x into 2 plus minus 2 into 7 is equal to 0. Here, x into 2. So according to this equation, where is x into 2? So some of you have missed the 2 here when you copied. But from your memory, you did it correctly and you got the answer. Okay. Define pH. pH is equal to minus log concentration of pH plus. Calculate the pH of a 1 molar SCl solution. That question. SCl. Assuming complete dissociation. H plus Cl minus. 1 mole. 1 mole. 1 mole. You are given 1 molar solution. So, if there is complete dissociation, from 1 molar Cl, you will get 1 molar H plus and 1 molar Cl minus. Now we calculate the pH of the solution. pH is equal to minus log concentration of H plus is equal to minus log what is concentration of H plus, that is 1 molar is equal to 1. This is equal to minus log 1. Dixie ma'am was teaching you. Log 1 is equal to anybody, Adul. What is the value of a log? 0. 0. So minus 0, that is equal to 0. So pH of the solution is equal to 0. pH of the solution is equal to 0. Okay. Some of you have written this one, 10 raised to minus 6. That is from the notes you have copied. You have copied at 10 raised to minus 6. So that the pH is equal to 6. You have written that. And I think it is copied from the notes, I think. Bronsted theory of acid and base. Yes. Acid, proton donor, base, proton, acceptor, conjugate pair. A pair of acid and base, which differs only in one end. The correct answer is one proton. But one of you, some of you written, which differs only in one pair of electrons. One pair of electrons, you are written. That is wrong. That is not a conjugate pair. It is a one proton, not electron pair. You can remember how many of you written pair of electron, not electron. It is not the electronic concept, it is the protonic concept. Then what are conjugate acid and base of NH3? NH3. You are given NH3. And you have to find out the conjugate acid. How do you get the conjugate acid? You add H plus. H plus. Then you will get the conjugate acid. So NH4, there is plus charge. And this is the conjugate acid. Conjugate acid of ammonia. Conjugate acid of ammonia. And what is the conjugate base of ammonia? NH3 How do you get the conjugate base? Atul has written this correctly. Minus H plus. From that, you subtract 1H plus. So you will get NH2. H plus is removed. So this will be having minus charge. NH2 plus H plus is equal to NH3. NH2 minus plus H plus is equal to NH3. So NH3 minus H plus, you will get NH2 minus. And this is the conjugate base of ammonia. Both of ammonia. So if you are given a species plus H plus, that is conjugate acid, minus H plus, that is conjugate base. When H plus is added, there will be positive charge. Okay, let me ask you another question. Say you are given HCO3 minus. What will be the conjugate acid of this? Conjugate acid. Steffi, can you say conjugate acid of HCO3 minus? You add H plus. Then what will be? You add all this. You will get H2, CO3.
CO3.
Charge will be there, plus and minus cancelled. So H2CO3, that is the conjugate acid. Okay. Then what is the conjugate base of this? HCO3 minus. It's a conjugate base. Minus H plus. H plus. One hydrogen is removed. So what is left? CO3. When H plus is removed, see here, a negative charge is created. There is one negative charge already. And a new negative charge is created by the removal of H plus. So the total charge will be minus 2. Two negative charges. So CO3 minus 2. Or you can write it as CO3 2 negative like this also. That is the conjugate base. Okay. You are asked to find out the conjugate acid in the base of ammonia, only ammonia. So you add H plus and subtract H plus. Then you will get the conjugate acid and base. All right. Okay. Now let us proceed with the optical isomerism. Proceed with optical isomerism. 11:30. Okay. So let us continue with the optical isomerism. Okay. Let me repeat the whole things we have seen the last day. First, we have to see plane polarized light. The light consisting of photons vibrating only in one plane, that is plane polarized light. When plane polarized light passes through solutions of certain compounds, the plane of polarized light will be rotated, shifted. And that phenomenon is called optical activity, and such compounds are called optically active compounds. Now you come to optical isomerism. The isomers which rotate the plane polarized light in the opposite direction, plus and minus directions, right and left, in the opposite direction, they are called optical isomers. And that isomerism is optical isomerism. Say there are certain optical isomers which can exist as non-superimposable object and mirror image. Non-superimposable object and image. Such optical isomers are called enantiomers. And that optical isomerism is called enantiomerism. Enantiomerism. If the object rotates the plane to the right side, then it is called right hand side. Then it is called dextroisomer or d-isomer or plus isomer. Plus isomer. And if the isomer rotates the plane of the light to left side, it is called a isomer or small l isomer or minus isomer. Minus isomer. You take a mixture of a D and L, equimolar mixture of a D and L. Equimolar mixture, equal number of molecules. Then it is called DL form or DL isomer or plus minus form. Plus minus form. Or it is called racemic form. Racemic form or a racemic mixture. The racemic form is optically inactive. See, D form is optically active. L form is optically active. You take an equimolar mixture, that is a racemic form or a plus minus form or DL form. That is optically inactive. The racemic mixture is optically inactive. There is no resultant optical rotation. And that is due to the compensation. External, we call it as external compensation. External compensation. External compensation of the rotation. Say the D isomer rotates the plane to plus theta. And that light is rotated by the L isomer to minus theta. So that, see, I shall show you that. See, here, light is passing like this. This is the original position of the rotation, suppose. Now, here there is the D isomer. Light passes through the D isomer. Then what happens? The light is rotated. Light is rotated to, say, right side like this. That is the D isomer. Light is rotated to this. This was the original plane. So it is rotated to right side. Now, this light passes through the L isomer. Then what happens? This light, this rotated light is again rotated to left side to the same angle. So what will happen to the resultant, the emergent light? So it will be having the same rotation. See, rotation. That is the thing. Here it is rotated to plus theta. And that light is again rotated to minus theta. Say minus theta. So it comes to the original plane. Got it? So there is an external compensation. Compensation outside the molecules. And the DL form, racemic form, is optically inactive due to external compensation. All right. I had taken an example, lactic acid. There is a lactic acid. So it is CH3, CHOH, COOH, lactic acid. You know the structure of a lactic acid. Say H. Here there is a CH3, and here there is a OH, and here there is a COOH. Structure of a lactic acid. CH3, CHOH, COOH, lactic acid. Okay. We can show that by drawing a cross like this. And it is called the Fisher projection. Fisher Fisher projection. He used a cross mark like this. Say at the meeting point, at the junction, the crossroad junction. Crossroad junction, there is the central carbon atom. Central carbon atom. And here we have a COOH. And here there is a CH3. Here there is a OH. Here there is H. Now you take the mirror image. The mirror image. There is lateral inversion. Lateral inversion. Left and right sides will be changed. So that COOH and here there is a CH3. That is the image. Now, you just slide these two structures. Suppose this is the object. This is the first one. First one. Say, let it be the object. Before that, this is the object. Suppose. Object. Then this is the image. The image. Okay. Then, suppose the object is the D isomer. Suppose that is D lactic acid. Suppose lactic acid. Then the image will be L lactic acid. Lactic acid. We decide which is D and which is L. Only that much. Only that much. If the object is the D form, then the image is the L form. Okay. And these two are non-superimposable. If you slide these two, you just keep the image over the object. Keep the image over the object as such. As such. Say carbon and carbon will be coming in the same position. OH and OH will be coming in the same position. H and H will be coming in the same position. But what about CH3 and COH? They are not identical. Similar is the case with the other side also. So the identical groups, similar groups, are not covering the similar ones always. All the similar groups or atoms are not covered by the image. The image cannot cover the similar atoms or groups on the object. Then we say these two are non-superimposable. There is one condition. Remember that you cannot keep the front side back. You just slide, that's all. Slide both, that's all. That is the condition given by Fisher. It is not a planar molecule. Actually, this is not a planar molecule. Okay. Now, if these two are not superimposable, these are non-superimposable. Non-superimposable. If the two structures are non-superimposable, then we say the molecules are chiral molecules. These are called chiral molecules. Chiral molecules. Or they are called asymmetric molecules. Asymmetric molecules. They are called as dissymmetric molecules. Chiral molecules or asymmetric molecules or dissymmetric molecules. You remember the chiral molecule or asymmetric molecule. If these two structures are non-superimposable, a molecule is not superimposable on its image, then the molecules are called chiral molecules or asymmetric molecules. And the phenomenon is called chirality. So these two molecules, or a lactic acid molecule is a chiral molecule. This is optically active, I told you. You know, optically active substances are chiral molecules. Always Optically active molecules. Optically active molecules will be optically active molecules are chiral molecules. They are chiral molecules. Only chiral molecules are optically active molecules. So the D form and the L form both are chiral molecules. Okay. Now you come to the central carbon atom. See here, this carbon atom. Come to the central carbon atom. The central carbon atom is bearing four different atoms and groups. You take the you take the atoms and the groups. See here, attached to the central carbon atom. This is our central carbon atom. This one, central carbon atom. Valence of carbon is equal to 4. That we know. Valence of carbon is equal to 4. And the 4 valencies are satisfied by 4 different atoms or groups. So the central carbon atom has 4 different atoms or groups. 4, remember 4, compulsory 4, not 3, not 2, 4 different atoms or groups. Carbon atom with the 4 different atoms or groups. That's called chiral carbon. That is called chiral carbon or asymmetric carbon, or it is called the chiral center or asymmetric center. A new term is coming here. Today I have introduced chiral. That is the only thing introduced today, chiral. So what is meant by chirality? If the objects and the mirror image are non-superimposable. A molecule is non-superimposable on its image. The image is non-superimposable on its object. Then it is called chirality. Such molecules are chiral molecules or asymmetric molecules. Optically active substances are chiral molecules. They are asymmetric molecules. Now you come to this chiral molecule, lactic acid. In the lactic acid, it's a chiral molecule, asymmetric molecule, optically active molecule. You take the central carbon atom. The central carbon atom are having 4 different atoms or groups. Central carbon, hydrogen, COH, OH, CH3. 4 different atoms or groups. It is called a chiral carbon or a symmetric carbon or chiral center. Chiral center. So chiral center means the carbon atom bearing 4 different, I repeat, 4 different atoms or groups. Say, let me take a carbon atom, say like this, double bond O, say OH, and there is R. You take this carbon, you take this carbon. Now you say whether it is a chiral carbon or not. Nandana, what is your opinion?
No, sir.
Carbon, Mark?
No.
No. No. Why not? Say the groups are OH, there is oxygen, and there is R. Different groups are there.
3 atom groups.
3 are there. Only 3 are there. There should be 4 different atoms or groups. Okay. So this is not a chiral center. That carbon is not a chiral carbon. There should be 4 different atoms or groups. Then it is a chiral carbon or a symmetric carbon or a chiral center. In the optically active organic compounds, there will be chiral carbons or asymmetric carbons or chiral centers. Okay, as it is seen in the case of lactic acid. Let me stop.